Yes, the recording has been started. So after all those adventures, let us, I think it's very appropriate that all kinds of things go wrong during the lecture, which is essentially supposed to be dedicated to things that can go wrong. So today we are going to talk about threats to validity. So validity is, of course, a major concern for any kind of research, any kind of empirical research in particular. And it's important to understand that validity is not something you can do after you have conducted your experiment. Validity considerations are equally important during the design phase as during the execution phase. So what does actually validity mean? So validity should be adequate. So this means that the result should be valid for the population of interest. Of course, we need to understand that any empirical study has its threats to validity, has its limitations. We are going to see in a moment what those are. And in fact, discussing those threats does not diminish the value of your study. In fact, it increases the value of the study because it clarifies the scope where the results can be valid. So we talked a little bit about the population of interest. So you probably remember those images from our lecture on sampling, right? So we have our population of interest. We have a sample that has been derived from the population, but we can also go beyond this particular population. So let us look at the example. For instance, we can be interested in understanding open source projects. So of course we cannot study all open source projects imaginable, so we determine the 25 projects that we actually want to study. So in this sense, those 25 projects will be our sample, while the collection of all open source projects in the world will be our population. Still, it is plausible, or at least we hope, that some of our conclusions might be generalizable beyond open source software to other source or software development models. Then we will be actually going beyond the population of our interest. As opposed to this example, adequate validity does not necessarily imply some kind of ultimate generalization. So we can, for instance, conduct an experiment within an organization, and we might be designing this experiment to answer some questions which are actually specific to this organization and are not even necessarily interesting for other organizations. Of course, if we are deriving conclusions which are supposed to be going beyond the limits of our organization, then they should be applicable beyond the specific context. So when discussing threats to validity, essentially, we need to understand what can go wrong. What can go wrong in a sense that the study, based on the sample itself, might be invalid, or that the sample might not be representing the population from which is drawn, or we will not be able to generalize our conclusions beyond the population that we have studied. So in the very, very first attempt to classify different kinds of threats to validity, we can distinguish between internal and external validity. So roughly speaking, internal validity is related to the conclusions which are derived for the study itself, while external validity is related to generalizability of the findings. So if, for instance, we have applied a wrong statistical method, then would be related to the study itself, while if we can, for instance, say that we have only studied students and the results are not necessarily generalizable beyond this to a general software developer population, then this would be an threat to external validity. Claes Wohlin and his co-authors have proposed a more refined classification of threats to validity in contract, internal, conclusion, and external threats. So what we are going to do now, essentially what we are going to do in the largest part of the lecture, we are going to position those 4 groups of threats to validity, and we are going to see many examples of different kinds of threats. So Wohlin has been looking at conducting experiments, but most of the discussion is also related for any kind of empirical studies. So for example, let us take an example, right? So let's assume that we have a theory which says that it takes more effort to maintain complex source code. So in this sentence already, there are 2 theoretical concepts. One is a concept of complexity, another one is a complex of effort. So the cause construct would be complexity of the source code, and the effect construct would be the maintenance. The effect construct would be the maintenance effort. So if you would like to evaluate this theory empirically, and don't forget that empirically means based on observations, so we need to some kind of representation of those 2 theoretical constructs at the level we can observe. So for instance, if we are talking about source code complexity, we can think about cyclomatic complexity. Or we can talk about CK metrics that Dario Dinucci has mentioned last week. Or we can talk about complexity of the identifiers. On the other hand, when we are talking about operationalization of the effect, we can, for instance, think about measuring time that participants in our study need to perform a specific maintenance task. So in this case, we have operationalization of the source code complexity construct as a collection of metrics. This is a treatment. And our output then becomes the amount of time that the participants need to perform a maintenance task, which is an operationalization of the effect construct. All those errors can be associated with all kinds of things that can go wrong. So the first group of threats is related to translation, to operationalization of those theoretical constructs to things which we can observe. So we need to ensure that the treatment actually reflects the construct of the cause. For example, we need to ensure that those metrics represent source code complexity, and we need to ensure that time represents the effect. And what go wrong here is, for instance, that if I'm operationalizing effect as time in an uncontrolled setting, we cannot necessarily be sure that this time is actually being spent on the maintenance task. Maybe our software developer just took a break to drink coffee and our time is still running. In the same way, if we are operationalizing source code complexity as cyclomatic complexity, then maybe we are not taking into account complexity which is induced by poor variable naming or lack of documentation. So all those things can be related to complexity. Good. The next group of threats is related to external validity. As I already mentioned, external validity is concerned with generalization. So if there is a causal relationship between the construct cause and the effect, can the result of the study be generalized outside the scope of our study? So for example, is there a relation between the treatment and outcome? So let's go back to our example of source code complexity versus a maintenance effort. In this case, external validity can be, for instance, threatened if our conclusion was based on analysis of a couple of very small open source systems, while the generalization is pretending to make the claim of a causal relationship for any open source software system. So if we have a very small study which is somehow not adequate for a much larger population, then we cannot generalize our conclusions. Conclusion validity is about relationship between treatment and output. And this is a kind of validity which is related to statistical relationship. So essentially, we want that we want to see sufficient argument, sufficiently strong argument that there is indeed a relationship. So for example, we discussed the situation when we are applying statistical tests, and those statistical tests have assumptions which we did not check or which might have been violated by our data. This would be a threat to conclusion validity. So conclusion validity is most often about statistics or related concepts. And finally, the last type of internal validity is again about the relationship between treatment and output, but this time it's essentially about causality. Is it possible that the relationship we have observed cannot be attributed to causality, but for instance to a factor we have not observed? So it is essentially much more about the design of the experiment itself. Typical factors that impact the internal validity are, for instance, how the subjects are selected to different or divided to different classes, or how are they being treated, or how they're being compensated. So we are going to talk about the impact of compensation on validity. Is there something happening when independent from your experiment, which might, for instance, distract people? So all those factors can cause the experiment show a behavior which is not real in a sense, which is not due to the treatment, but due to some kind of disturbing factor which we do not control. So let us make this entire story of threats to validity a little bit more tangible. So you might remember the study from Kruger from the first lecture. So what happened there, just to remind you, the authors used fMRI to study whether code writing and prose writing are similar in terms of neural activity, so essentially in terms of Brodmann area activations. You might remember that the question that the authors tried to answer was, do different types of writing exhibit the same patterns of activity? So in this particular study, we can identify multiple types of threats to validity, at least 3. So on the left, on the yellow background, we see a concern which is related to the organization of the task. So during the task, participants have been given an assignment to either fill in the blanks in source code or in prose, or to write essentially small technical exercises or small pieces of prose. So like, for example, one of their long response assignments is sorted, right? So participants were requested to write a function which returns true if the input vector is sorted. So obviously, this is not typical. This is not how software developers typically work. Usually they work with much larger code bases, which is consisting of multiple interrelated components, and performing maintenance tasks requires much more elaborate thought than what those small examples might suggest. So this can be seen as a threat to construct validity, because the abstract notions of this construct of writing code does not necessarily is not necessarily correctly captured by the experimental tasks. So this relationship between the theoretical concept, between the construct of writing code and specific tasks or specific measurements is related to the construct validity. On the right, in the blue side, you see a concern related to correctness of measuring the neural activity. So, as I mentioned, the participants have been provided with code snippets where they were required to fill in the blank, or with text which described what kind of functionality they need to implement. So this means that before writing code, participants were required to read either code in case of the fill in the blank code scenario, or merely text if they were supposed to write new functionality. So this means that the measures of the neural activity which have been performed during the study also reflect the reading part and not only the writing part. So to address this threat to validity, the authors have actually performed a contrasting experiment. So their fMRI were subtractive, such that they essentially compare the long response for code versus long response for prose, such that essentially the part which is related to the reading can be cancelled, because whether you are writing a piece of text given the task, or whether you are writing a piece of code given the task, you need to read the task description anyway. So the threat here was the threat related to internal validity, specifically to instrumentation, to how do we perform our measurements, and it has been taken into account during the design phase. Finally, this the block with the pink background in the middle is a threat to external validity. In this particular experiment, you might remember that the authors have decided to focus on native speakers who have a basic programming skill, so essentially they had one programming course as a background, and on the individuals who are right-handed. The reason why they wanted to do it is to ensure their ability to derive conclusions, because for non-native speakers, such as most of us, processing language might activate different Brodmann areas than for the native speakers, so might activate those areas in different way. So in order to ensure their internal validity, the authors had to sacrifice generalizability. They had to sacrifice external validity a little bit, in the sense that conclusions they have derived do not necessarily generalize to non-native speaker, left-handed individuals, or professionals with years of professional experience. And this opposition between internal and external validity is quite common. So we are going to talk about it later on during the lecture. And now it is up to you. In this particular study, researchers have asked 6 experts to evaluate modularity of several software systems. The discussion revealed that experts A, B, and C interpreted modularity as coupling, while experts D, E, and F interpreted modularity as cohesion. So according to you, this threatens construct validity, external validity, conclusion validity, or internal validity. And you have a summary of the 4 types of validity on the slide. Please start. Okay, okay. So what do we have? We have three responses who are saying A, it's a construct validity. Two responses saying C, it's a conclusion validity. And one response saying D, it's an internal validity. So in this case, it is a threat to construct validity. The reason is that the modularity construct, so the theoretical notion of modularity, has not been adequately explained, has not been adequately clarified to the experts, ultimately leading to different interpretations of the same concept. This is the problem which is known as inadequate pre-operational explication of constructs. It's a whole mouthful, but essentially it means that the constructs are not sufficiently defined. If the constructs are not defined, if the theory is not clear enough, then the translation cannot be sufficiently accurate. So if you are, for instance, comparing two ways of performing software development, and we want to check which one of them is better. But as long as we do not really clarify what better means, this question doesn't really have any sense. Doesn't make any sense. Do we want, for instance, to develop software faster? Do we want to develop software which is more reliable? Do we want to develop software which is more user-friendly? And so on and so forth. So the concept of better is not adequately explicated. Okay, another example. The same picture on the left, on the right, a slightly different story. So in this case, we have researchers who applied the students' t-test, but did not verify whether the samples compared are likely to have been drawn from a normal distribution. So this would threaten, again, the same four: A, construct validity; B, external validity; C, conclusions validity; and D, internal validity. Okay, so good news is nobody thinks that this is external validity. It is not external validity. One person thinks it's a construct validity, two people think that it's conclusion validity, and three people think that it's an internal validity. So what's going on here? First of all, it's not a construct validity. So for construct validity, we need to have some kind of theoretical construct which has been correctly or incorrectly operationalized. There's no discussion of any kind of operationalization here. This distinction between conclusion validity and internal validity is more annoying, in a sense that some people interpret internal validity in a broader sense of the world, like all kinds of things which can go wrong. We are using the classification of Wohlin that separates things which are related to conclusion validity, to statistics and related measurements, to the notion of conclusion validity. So in this particular case, assumptions of the statistical test might have been violated, meaning that it's a threat to conclusion validity. So why do we actually need all this discussion? Typically, threats to validity play two roles. We either can improve our study design during the design phase by reflecting on what can potentially go wrong, or we can try to understand the limitations of our work. I already mentioned when we talked about the experiment of Kruger that because of this issue of reading the task, they have designed the experiment in a contrastive way. So this is a scenario, this is an example of a situation when the researchers have been thinking about threats to validity in advance, and they have designed their experiment to reduce the impact of those threats. At the same time, there are, of course, threats which you cannot just address. So you need to understand the emissions. Again, the same study of Kruger. They only looked at native speakers with limited programming experience and who are right-handed. So those are the inherent limitations. It's important to understand that those inherent limitations cannot be used as an excuse. It's not an excuse not to improve the design as much as possible. So remember our example with this maintenance of the source code versus the effort, right? So when the complexity of the source code versus the maintenance effort. So we have decided to operationalize the maintenance effort by looking at time, and the problem was that developers might be taking a break. Alternative to this kind of design might have been to consider to moving to a controlled experiment. For example, instead of letting developers work at their home, at their own in their own environment, we can invite them to the lab and observe them while they're working in the lab. Since they're working in the lab, we can be sure that they're not taking a break and not going to take coffee. But of course, this lab, this artificial environment might make them less comfortable, meaning that the results of our experiment are more likely to exhibit stronger internal validity, right? We don't have, they have more control, but lower external validity. We cannot generalize because maybe this is behavior we see only in the lab setting. Yet another way would be to continue the maintenance effort, not by looking at the clock, but by eye tracker measurements. So on the slide, we see an eye tracker data, which shows us at which parts of the source code the developer was actually looking at. And it's a heat map, right? So the redder the part of the image, the more attention was going to this particular part of the source code. So in this image, we essentially see that most of the attention of the study participant was going to something like if large format, int buff equals being assigned to 0, and so on and so on. This information can be used as an indication of attention or maintenance effort as opposed to some kind of source code metrics we want to measure. Good. So what we are going to do now, we are going to review the 4 categories of validity. We are going to start with the construct validity. And for each one of them, I am going to list several examples of things that can go wrong. Those examples are common, but they're not necessarily exhaustive in a sense that your specific setup, your specific study is very likely to use threats which might not necessarily fall into one of those defined types, but many of them do. So those are very, very commonly observed threats to validity. Specifically, when we are going to talk about construct validity, we are going to distinguish between the design threats and the social threats. So design threats are issues which are related to the design of the experiment. Essentially, we can typically take them into account while designing the study. And it is all about ability of our study design to reflect what we essentially want to measure. The social threats are concerned with issues which are related to the behavior of our study participants. It's crucial to remember that study participants are human beings. And this is very strange for me to say, but experimenters such as we should not forget that participants have their own free will. And in a sense, they can always act differently simply by the virtue of the fact that they are participating in a scientific experiment. And of course, we would like them to behave as naturally as possible, but this is not always the case. So let us start. The first type of construct validity threat is the one we have already seen: inadequate operationalization of explications of constructs. So the constructs are vague, they're not sufficiently defined. We are talking about better software development, we are talking about modularity. They cannot be adequately translated to measures or treatments, and this is why the validity of the construct validity is threatened. Another example is a confounding constructs and level of constructs. Again, it's a fancy name for a relatively simple situation. Sometimes it's not primarily the presence or absence of a construct which is important, but the level of a construct. So not merely a distinction between black and white, but distinction between different shades. For example, we can say that the absence of prior knowledge in programming language might cause the observations during the experiment, but actually it's not so much absence or presence, but rather how many years of programming experience the participants have. So we can have a much more fine-grained situation and a much more fine-grained analysis of what is essentially going on. So it's important to distinguish between presence or absence of a construct and the levels of the construct. Interaction of testing and treatment. This is an interesting one. So the testing itself can make our study participants more sensitive or receptive to the treatment. So let me give an example. Let us say we are still in the setting of source code complexity versus the maintenance effort, and we are measuring time. And let us say that as part of our experiment, we are showing the participant the time is that it takes them to perform the task. And we tell the participant that it is important to perform the task as fast as possible. So essentially, this means that the participants are getting pressured, right? So suddenly they might be sacrificing, for instance, correctness in favor of the speed. So in this particular way, we can essentially be confusing the treatment, which is essentially source code, main complexity, and the impact of testing. So the way we actually conduct the evaluation. Sometimes our participants are actually involved in multiple studies. And there can be interaction of multiple treatments. So for example, let's say we want to study the impact of continuous integration on pull request resolution. This was actually a topic of Nathan's master thesis. Introduction of a continuous integration solution, such as Travis CI, could be seen as one of those treatments. Participants in our case are open source projects. What happens if during the same experiment our participants were subject to a different treatment? For instance, they have introduced a bot. They introduced a code review bot. From the literature, we know that introduction of code review bots can also affect the pull request time. So in this particular case, for projects that have both introduced continuous integration solutions and code review bots, we might see interaction of those treatments on the variable of our interest, so on pull request resolution process. So this means that if we are analyzing our data, we need to be aware of possible additional treatments that have been performed to it. And since it's not a real experiment, but a quasi-experiment, you cannot always exclude this. meaning that you need to be careful in selecting the data. The next type of a construct validity is the mono-operation bias. So, if the experiment includes a single independent variable, or a single subject, or a single treatment, the experiment may actually underrepresent the construct and does not give a full picture of the theory. A related notion is a notion of a mono-method bias. So it's very similar to the mono-operation bias, with the difference that instead of looking at the treatment side, mono-method is looking at the outcome side. Specifically, if you are talking about we are using only one measurement technique to perform our measurements, we might get misleading results. So, for example, if we want to measure the number of faults in some kind of code review experiment, and the fault classification is based on a subjective judgment, then the relations cannot necessarily be sufficiently explained. So a typical solution to this kind of problems would be to involve multiple measures which are reflecting a construct or are somehow complementary to each other. The last example in this category is restricted generalizability across constructs. So the problem here is again with it on the treatment side. So the treatment may affect the studied construct positively, but it can unintentionally affect other constructs negatively. And this might be hard to generalize into other potential outcomes. Again, let us make it a little bit more tangible. So let us say we have a comparative study which is concluding that improved productivity can be achieved with a new software development method. However, it can also be, the researchers have also observed that this new software development method reduces maintainability, which is, of course, an unintended side effect. So if the maintainability is not measured or not observed, then there is a risk that conclusions which are drawn based on the productivity attribute would be ignoring the maintainability. So this might suggest that in the long run, benefits of the increased productivity can be threatened, can be eaten up by productivity loss due to maintenance issues. I see that it's 9:30. I just would like to discuss with you 3 social threats to construct validity and ask you a question which you can reflect upon during the break. So what are our social threats? The first one is related to hypothesis guessing. As just to remind you again, social threats are related to the fact that the participants are humans and they behave not always in the ways we expect. And hypothesis guessing is one of those. When people take part in an experiment, they might consciously, or intentionally or non-intentionally, try to figure out what the purpose and the intended result of the experiment. So for instance, if you're showing them 2 types of source code, they might somehow figure out which of those 2 examples have been produced using our new approach, and they might guess that our hypothesis is that our new approach is more beneficial than the existing one. It's not always the case that the guesses influence behavior in a positive way. They can also guess them in a negative way. So how can one deal with this? First of all, some researchers introduce extra measures to try to hide the goal of the study, or even to explicitly deceive the participants. So deception in a scientific experiment is a controversial method, but sometimes it is unavoidable. For instance, if you want to study the impact of previous education or previous experience on fishing practices, this would require you actually to send phishing mails to study participants. And if you want to send phishing mails to study participants, and you are, logically speaking, deceiving them because you would like them to exhibit a certain behavior without having a complete knowledge, so essentially without knowing that those mails are phishing mails. The next example is evaluation apprehension. Some people essentially are afraid of being evaluated. And study participants might feel that they are failing the experimenter if they are performing the task in a certain way. So obviously the experimenter should stress that there is no evaluation of the participants, but merely of the techniques, but still. This can go other way around as well. So there is also a human tendency to try to look better when being evaluated. And this can also confound the results. So for example, let's say we are working with two different effort estimation models. We ask our participants to report deviations between their efforts they have estimated and the effort which has actually taken place in practice. Some participants might try to improve their estimates in order to look better in the eyes of the researcher. And finally, there is also a matter of experimental expectancies. The experimenters, us, can influence the study both consciously and unconsciously through their expectations. We as experimenters know what we would like to observe because of hypothesis. And we can induce a certain behavior on the participants. How to deal with it? One way would be to use proxies, so essentially to involve different people rather than researchers to conduct the experiment itself. In this case, the proxy would not necessarily know what hypothesis is being tested, but of course the proxy will know the experimental protocol, so essentially what are the study participants supposed to do and when. Another way would be to try to use a mechanism which would be compensating for those expectations. For instance, to always stick to a predefined script, such that at least there will be no explicit differences in how experimenter behaves with respect to different participants. Good. So this would be our question for the coffee break. On the upper part of the slide, you see a slide representing a triangulation. So in that particular study, the authors have performed statistical analysis based on a large-scale data sample and a survey. So they have obtained different participants on the same questions they wanted to get answered. So this is what is called triangulation. And the question to you is, which one of the threads on the slide can be addressed by the triangulation? A, hypothesis guessing. B, interaction of different treatments. C, confounding constructs and levels of constructs. And finally, D, a monomethod bias. You have till 9:45 to answer this question and to enjoy your coffee. So from our surveys, from our poll, we got 2 answers B and 2 answers D. So when we are talking about threats being addressed by a certain technique, we mean threats being reduced using this technique. So in this particular case, triangulation reduces the likelihood of a mono-method bias. We are using multiple techniques to answer the same question, to address the same concern. Interaction of different treatments. So triangulation is, of course, about 2 different ways to derive the same conclusion, or derive complementary conclusions. It's not necessarily a treatment. In particular, when we are talking about repository mining, we are analyzing their data coming from a software repository. We are not really treating this data, right? We're just observing what is going on. With the survey, of course, the treatment is much more explicit, but it's not really an interaction of different treatments. Yari has asked in the chat whether isn't there also here the subjects are informed of the hypothesis, or is it just a better for not part of a social construct validity? Well, it's not social. Well, it's social construct validity. It's a kind of group, right? Specific threat. Usually, participants do not know to what hypothesis we are testing because of the social desirability bias. So essentially, if we are very explicit about what we want to establish, participants are more likely to conform to our expectations, right? So it's related to those expectations. Rather than to exhibit a more natural behavior, we are actually would actually like to observe. Can we imagine a situation when participants will be informed about the hypothesis we are testing? Maybe. I don't have an exact answer at the moment, but we need to reflect on this. Okay, so let's continue. The second group of threats to validity is external validity. And luckily, there are only 3 large categories here, which are related to interaction of the selection and treatment, interaction of setting and treatment, and interaction of history and treatment. Let us check them one by one. So interaction of selection and treatment simply means that the subject population is not representative for the population we want to generalize to. So our participants are somehow wrong with respect to the population. So they exhibit behavior which we would not observe for the population we would like to study. There is an ongoing controversy on employing students in software engineering studies as proxies for professionals. And this is essentially a kind of threat which is induced by replacing professionals by students. Interactions of setting and treatment is essentially related to experimental setting. In the same way as selection versus treatment is about selecting wrong people, setting versus treatment is about selecting a wrong practice or a wrong experimental setting. An example it would be that we are using an old-fashioned tool in an experiment when there are much more up-to-date solutions which are commonly used in the industry. Or, for instance, adding toy problems in the experiment. So in a way, the setting refers to wrong place or wrong environment or wrong technique or wrong experimental object like source code, which are not adequate for what we essentially want to achieve. And the last group is related to interaction of history and treatment. So this is related to the fact that an experiment is conducted on a specific time or a specific day, and this can influence the results. So, for example, we want to study a safety critical system, and we happen to run a questionnaire a few days after a major software-related crash, or happen to run our survey a couple of days after a major security breach, which has been highly publicized on social media. So this kind of events are likely to affect the perception of our participants, and as such, we might be getting different answers compared to a situation when if you would have asked exactly the same questions a couple of days before or a couple of months later. So again, external validity is all about generalization, about choosing wrong people, choosing wrong methods, objects, or a wrong setting, and finally choosing a wrong time. Well, choosing, it's not always choosing, but it's related to the wrong time. So to address those threats to external validity, we would like to have realistic situations. We would like to have generalizable situations. You might remember that realism and generalizability are not exactly the same. And moreover, it's not always possible to make to create such a generalized and generalizable situation for certain kinds of studies. For instance, for controlled experiments, it's not really possible. And of course, reality on itself is also not homogeneous. So saying we need to create a realistic scenario is easier to say than actually to do. Conclusion validity. So as you might remember, conclusion validity was related to the ability to draw correct conclusion about relating the treatment and the outcome of the experiment. So most of the time, conclusion validity is related to statistics. We have already seen an example of a valid assumption of statistical data, right? You remember this discussion of normality assumptions, not normality assumptions, and so on. Two other examples are so-called low statistical error and phishing and error rate. So I'm not going to discuss the low statistical power too many details. If you are in of statistical power, please check your books on statistics. Essentially, if the power is low, this means that there is a high risk that we derive an erroneous conclusion. Phishing error rate is related to essentially searching for a specific result, because the analysis we are conducting are no longer independent, and we essentially can be influencing the result by looking at specific outcome. Error rate is related to the discussion we had about adjustment of p-values, right? When we conduct studies, when we conduct multiple, for instance, when we ask multiple questions, and the error rate is essentially the likelihood that we are going to report at least one error. Okay, the next question is the next group of issues here. Okay, couldn't I repeat my last sentence? Yes, so the error rate was related to the errors which are induced by repeated tests, by repeated experiments. You might remember when we talked about statistical analysis, we also talked about adjusting p-values. So the error rate is essentially the likelihood that we report at least one erroneous conclusion. Reliability. So reliability is related to measurements, and reliability is related to implementation of treatment. So when it comes to measurements, for instance, things like a poor question wording or a bad out or bad interpretation can affect the results. Ideally, when you measure the same phenomenon twice, you should obtain the outcome. This is, of course, not always the case. So if you're going to measure the number of lines of code in a source software system, if you're going to measure it, you're going to obtain exactly the same number, at least provided by using the same measurement instrument. Sorry. If you are measuring something like amount of functionality which is implemented in the system using a function points approach, for those of you who have taken Software Evolution last year, they might remember function points. This is essentially a process which involves human judgment. So even if you take the same person and the same piece of code and ask to perform the same kind of computation, you might end up with different numbers. So this is reliability of measures. Reliability of treatments is essentially very similar, with the difference, of course, if you're not really measuring, but you're applying the same treatment to different people, or you're applying the same treatment to the same person at different occasions. So again, this is why it is important, for instance, to stick to a predefined script when you are conducting an experiment, because you are not necessarily obtaining reliable results if you are somehow behaving differently towards different people. The last part of conclusion validity is related to randomness, to all kinds of things which are outside of your control. So for instance, there is a noise, or there is an interruption during the experiment, and the person got distracted. And the last group is essentially randomness of random heterogeneity of subjects. So as I already mentioned, reality is heterogeneous. Essentially, this means that participants are different. So what can we do? We can try to limit variation due to individual differences, for instance, by looking only at students of a certain year and of a certain educational program. As opposed to it, if you would like, for instance, to conduct a study with practitioners, then it turns out that practitioners are, of course, different. They have widely different experiences, widely different expectations, so the randomness there would be bigger. So next, it is up to you. The question about conclusion validity. What aspects of conclusion validity are threatened if the interview is conducted in a room next to which is portrayed on the image on the slide? So it's essentially a room with a glass wall next to a computer and a copy machine. You might remember from the lecture about interviews that it's not a good idea to conduct an interview in such a room. The question to you now is, what kind of threat to validity might be induced here? Okay, so we have people saying that it's C and one person saying it's D. So indeed, random irrelevances in an experimental setting is a very, very clear threat here. Just imagine that that there is a random passerby waving at the glass wall, or somebody that might be noticed by through the glass wall. So very clearly, random irrelevances in the experimental setting is a threat to validity here. I'm not so sure about reliability of treatment implementation. I mean, as any interview you might have, they might behave differently towards different interviewees. So this would be a threat to reliability of treatment implementation. It's not necessarily related to the location. So this is not necessarily something I would be expecting specifically for this question. What could happen here is indeed that the interviewee might feel uncomfortable because exactly of this glass wall, because of the risk of being observed. And this comfort might affect reliability of the answers to the interview questions. So my answer here would be that answers A, reliability of measures, and C, random irrelevances in experimental setting are correct. There's a cost statistics going on, right? Okay, next. Next is the internal validity. So internal validity is a very big group. So you'll see lots and lots of pictograms, lots of icons. In general, threats to internal validity are influences that affect independent variables with respect to causality results researchers. Again, we distinguish between design and social. Specifically, we also distinguish between single group threats and multiple group threats. So single group means that we treat all our participants as a single group and administer the same kind of treatment. In case of multiple group threats, we typically have experimental group or experimental groups and the control, which is essentially not being subject to treatment. For single group threats, we will typically focus on problems in determining if the treatment caused the effect or something else. For multiple group threats, we actually have a control group to address this kind of challenge. The problem is to interaction between participating in single group, in a control group, experiment controlled, who is participating in the experimental group. And of course, social threat is human beings, human participants are autonomous actors, can behave in any reasonable or unreasonable way, and definitely not necessarily the way we as researchers expect them to behave. So let us start. If you have a single group, different treatments might be applied to the same object at different times. So there is essentially a risk that the history affects experimental results. For instance, our first experiment was taken a day after the holiday. Everybody was very relaxed, not very focused. Or we have conducted an experiment on a day when this major security breach has taken place, and so on, right? So this the same object, different times. Maturation is also related to time, but it is related not necessarily to specific time, but merely to the fact that the time passes. For instance, we have a very long experiment. Participants are getting tired. Participants are getting bored. So this is why in the beginning they are better in performing their tasks. At the end, they're performing their tasks in a less successful way. Alternatively, maybe they are learning during the experiments. In the beginning, their performance is worse than at the end. Actually, we talked about this when we talked about experimental design, about controlled experiments. Right? You might remember that we talked about counterbalancing. So counterbalancing means that some people start with tool A and then continue with tool B, and some people start with tool B and then continue with tool A. So those methods are designed to limit the threats of maturation. The next ones. So we have testing instrumentation. So in general, if the test is repeated, the subjects may respond differently at different times since they know how the test is conducted. So it's not related to them learning the technology. It's not related to differences between Monday after the holiday and the regular day during the year. It is related to the fact that they know how the test is conducted. Instrumentation, this is essentially the problem in the tools we are using to conduct the study. And those tools, the word tools should be interpreted in the most generic sense imaginable. For instance, Data collection forms, if we are doing code reviews, those are code fragments we are reviewing, and so on and so forth. Right, you might remember this picture. So when we've been talking about how to ask about gender, this was a question proposed by Greta Bauer. Are you male, female, something else specified? And we have seen that this question, while this question was clear and easily answered by the cisgender participants, it did not clearly separate birth sign, sex, gender, identity, and subsequently it was not reliable, right? So it's here we are not talking about generalization, we are not talking about any kind of statistics, we are talking about internal validity. So this measure is not reliable. The next two, statistical regression and selection. So statistical regression is a threat which is typically associated with a previous classification, with a classification of participants into experimental groups based on some kind of previous performance. So I know that, for instance, in some of the courses at our universities, students are being allocated to project groups based on their grade for one of the previous courses. In the same way, let's say we have participants which are supposed to be given a software development task, but to allocate them to specific task groups, we check how they perform a training and then another development task. So this is essentially, this might become problematic if we are thinking about top 10 or bottom 10 or something along those lines. For example, if you look at the bottom 10%, then it's very likely that not all of them will be still in the bottom 10 after the treatment. But it's not necessarily because of the treatment, but merely because of the statistical likelihood actually lack thereof to get always in the bottom 10. Definitely we are talking about a large population, right? I mean, if you have 1,000 people, it is not very likely that the very same 10 people will end up in the bottom at 2 different measurement times. This is a statistical regression phenomenon. Selection is related to essentially the impact of voluntary participation. Of course, we are very often relying on volunteers because we simply don't have any other way. But at the same time, volunteers can be expected to be more motivated or more open to scientific research or whatever. And as such, they do not necessarily adequately representing the entire population. This is very, very typical for interview surveys in open source, simply because there is absolutely no way for us to sample those people as non-volunteers, right? We cannot just tell you and you are going to answer my questions. And we typically do not have any idea what the opinions are of the non-respondents. Two last groups are related to mortality, right? Groups of threats related to mortality and ambiguity about causal inference. So mortality is, of course, not literal mortality, but merely the fact that participants decide to drop out during the experiment. In general, participants dropping out during the experiment is not necessarily a major problem. Participants are free to disengage. This becomes extremely problematic if representatives of a certain demographics drop out in a much more likely way than representatives of other demographics. So for example, if all senior reviewers in our code review study decided to drop out, then of course we cannot be sure about their opinions. The last one here is ambiguity about direction of causal inference. So many techniques we have discussed essentially can only observe correlation. So we can say that A occurs quite often together with B. But we don't really know whether A causes B, B causes A, or even X causes X and B. So essentially there is some kind of unknown factor at play. For example, the question we've been asking about high source code complexity versus maintainability as a maintenance effort. Well, maybe indeed source code causes high maintenance effort. Complex source code causes high maintenance effort. But maybe it is not really complexity of the source code, but complexity of the underlying problem. And then the complexity of the underlying problem causes, on the one hand, highly complex code, on the other hand, significant maintenance effort. Typical setting to address this kind of situations and many other types of internal validity threats is through experimental design, when you are introducing a controlled group in addition to the experimental group. And then the control group is not subject to treatment. So essentially, we can check, for example, what is going to happen with the top or bottom 10%, right? As a statistical regression concern. Of course, introduction as a control group might induce threats which are related to multiple groups. And of course, social groups, right? Social threats. So for multiple groups, the problem is usually interaction with selection. And interaction with selection means that two different representatives of two different groups, a representative of a control group, a representative of experimental group, are somehow behaving differently, not because of the treatment or lack thereof, but because of whatever other factors might be at play. Just to give you an example, right? So essentially what we can do, we can take any of those single group threats and look at it through this interaction perspective. So for example, selection maturation would mean that we have, let's say we have, essentially this would mean that different groups mature at different speed. So let's say we have two groups, each group applies one method, everything looks fine, but then it happens to be the case that one of the groups learns this new method faster than the other group, simply because of the learning ability. And essentially this means that the maturation process in those two groups plays in different ways. And the same for selection history. This would mean that different groups are affected by history differently. They might be affected by testing differently, and so on and so forth. Okay, let's move to the yellow side, to the social side. Here we have four different kinds of threats. So diffusion or imitation of treatments is simply related to the fact that people talk to each other. So members of the control group, for example, might know about the treatment from the experimental group. And depending on what they actually know, they might try to imitate the behavior of the experimental group. So for instance, we have a control group which is using a traditional software development, and the experimental group which uses test-driven development. If they talk to each other, then the control group might suddenly just decide to start with writing tests, right? It is their free choice to develop software in any way they want, and they might decide to imitate the experimental protocol. The next point is related to compensation. So if a control group is given a compensation for being a control group, as some kind of substitute for the fact that they are not getting treatment, this might affect the outcome. The same if the control group is taught something else than a new method as a compensation for not being taught the experimental method. This sounds a bit vague probably. But for example, there is a study of Beatriz Fernandez and her co-authors. So what they have studied is whether software engineering students enhance their conceptual modeling skills after a daily practice of mindfulness. So students were divided in two groups. One group practiced mindfulness for 4 weeks. This was the experimental group. Another group was a control group, which was trained in public speaking. So this is a compensatory treatment which was offered to the control group, essentially to hide a little bit the purpose of the study. However, one might still wonder whether public speaking might have still helped the participants, because by speaking in public, you are expected to be able to structure your thoughts. And structuring thoughts might actually be useful when performing conceptual modeling. So this is a situation when we have a compensatory treatment offered to a control group, which might affect the validity of the conclusion. Then we have two more situations: compensatory rivalry and resentful demoralization. Both situations are related to the feeling of competition between the control group and the experimental group. So in the first case, a subject which is receiving a less desirable treatment might feel as an underdog, and essentially they might be motivated to reduce or even reverse the expected outcome of the experiment. So again, we have a new fancy software development method, and we have an old awkward software development method. So people who are using this old awkward software development method might be extra motivated to do their best to show that this old method is actually not that awkward and quite competitive. And finally, resentful demoralization is exactly the other way around. It's a reverse, right? So a subject which is receiving a less desirable treatment might simply give up and might not perform as good as they would usually do. So this would overestimate the impact of the new technology. This can, of course, also work all the way around, right? So we can also say that merely being exposed to a new technology can encourage participants. So this will give extra boost to people who are using this new technology merely due to the virtue of it being new. Good. The question for you. This is again a quote from the paper by Beatriz Fernandez and her co-authors. Depending on their preferences expressed in an interest questionnaire, the participants were divided in two groups: the mindfulness group, G138 subjects, and the control group attending the placebo public speaking workshop, G2. So this decision induces internal validity threats related to maturation, diffusion of or imitation of treatments, resentful demoralization, and selection. And again, I'm not saying that those are the only threats which are induced by this design. Okay. Come on. Selection, D, resentful demoralization, C, diffusion or imitation of treatments, B, and maturation, A. Okay, so almost everybody thinks that it's indeed selection. One person thinks it's resentful demoralization. We don't really know anything about the relationship between those two groups to say something about resentful demoralization, but there is clearly a threat which is related to selection, depending on their preferences, right? So essentially, the participants have been assigned to the treatment versus control group based on their preference. So the threats would be related to selection. Okay, good. So in general, I hope you remember this car simulator. The more control we have about the situation, the more likely are we to reduce threats related to internal validity. In the ideal world, of course, we would like to have both control and generalization, but this will be difficult. So this is a summary of what we have talked about. We have four constructs, four elements: cause construct, effect construct, treatment, and output. And then we have four types of threats to validity, each one associated with the pictograms. Whenever you are going to prepare a study design, specifically when you are going to prepare a study design for your assignment 2, for your essentially your big design assignment for this course, please take a look at this slide and try to reflect on what kinds of threats to validity can be associated with your design. And this is useful not only to write a section about threats to validity, which is of course important, but it's mostly important when you are thinking about design of your study. What kind of threats can you reduce? What kind of threats can you exclude? What kind of threats you just need to accept? Ideally, of course, you would like to have all possible threats. I mean, we won't like to have no threats at all, so essentially we would like to reduce all of them. But we have seen that this is not possible. Methods such as controlled experiment can be very useful to increase internal validity, but they will typically sacrifice external validity. Methods which are going to generalization will be typically reducing internal validity. So for instance, large-scale data analysis, GitHub data analysis, repository mining will be typically limited to correlations rather than causality. In general, the importance of different types of validity threats depends on your context. So for instance, and this comes again from the same book from Claes Wohlin, says that if your goal is to conduct a theory testing, it is most important to show that there is actually a causal relation between the treatment and the output. And then, of course, that the variables in the experiment are actually measuring the theoretical constructs, because our goal is to test the theory. In a sense, external validity is probably not so interesting because you already have a theory which explains that you have a relation between cause and effect. In applied software engineering, this is usually not the case. Most of the time we are doing applied research, we don't really have this kind of encompassing theory which would predict what should happen. We are merely observing what is happening. In this kind of situations, internal validity and external validity are extremely important. Typically, we are not interested in only showing results for company X or project Y, but rather we would like to show the very same results for all companies or for all projects, at least within a specific application domain or within a particular size. So external validity becomes more important. Essentially, this sentiment is echoed by the work of Janet Sigmund and her co-authors. So they have surveyed software engineering researchers, and they counted how often people have indicated that internal validity is more important than external validity, that external validity is more important than the internal validity, or they do not have a preference. So those are the letters I, E, and N. So you see that external validity is important, and it is even more so for studies which are involving humans, because there is a feeling that humans are very different, and in order to generalize, we need to aim at generalization. You have seen this picture before. Different methods are, of course, associated with different validity threats. So, for example, a maximal precision on the laboratory experiment would typically mean that we are reducing threats to internal validity. At the same time, threats to external validity are abound. If you are looking at studies which are aiming in generalizability, such as sample studies, we will have external validity, but the internal validity will be sacrificed. The last point I would like to make is that very often scientific papers combine multiple studies exactly to counterbalance different validity threats. So in this paper conducted by, in this paper by Diné Ford, Justin Smith, Philip Gore, and Chris Parnin, the authors performed two studies. So first of all, they have conducted 22 semi-structured interviews. This is a fragment on the green. So what happened there? It's an interview, and as such, it can be associated with high internal and conclusion validity. But it is not necessarily generalizable, because they only interviewed 22 people, and because in this particular case, they've been looking for barriers for contribution of women in Stack Overflow, and they only interviewed women. So essentially, this means that if there are some kind of barriers which are applicable for people of any gender, they will not be able to separate them from those which are gender specific. So to address this threat, to address this challenge, they have performed a follow-up study, which was a survey. And in this case, since it's a survey, it's much broader, the external validity is addressed. And since in this particular case, they have talked to people of different genders, they're actually capable of separating gender-specific and non-gender specific barriers for participation. So this is where I would like to stop today. If you look at the slides from the lecture, you will also see a course overview. This is actually the course overview. The reason why I wanted to show the course overview today is because while it's not the last lecture of the course, it is my last lecture. So we are still going to have two more lectures in January, on January 7 and January 14. Both will be guest lectures. On January 7, Fabian Beck Dr. Fabian Beck is going to talk about software visualization. As you might remember from our first lecture, software visualization is one of the data analysis techniques which has been successfully applied to understand software engineering data. So it will be on the right side together with quantitative analysis, qualitative analysis, and different variants of machine learning. And on January 14, Dr. Michaela Kreiler is going to talk about her work as a consultant in the field of code reviews. So far, both myself and all our guest speakers have been academic researchers with more or less involvement in industrial projects. Dr. Michaela Kreiler will provide a complementary perspective. So she's a trained researcher. She has a PhD in computer science, but she's working quite for some time now in the industry. And I'm very curious to hear what her perspective would be on this topic. So thank you very, very much. I apologize for the quality of the audio. If you have any questions, feel free to ask them on Slack. Goodbye.